You going for the platinum yet?
What?
You going for the platinum yet?
The platinum banana.
What's better for you?
Yeah, it should be. You know what that big thing was?
We just played it last time.
Oh, really?
I saw him in the face play.
We're rolling. No more bad words, we're rolling. Funny enough, our lesson is about liquids.
What kind of liquid?
Not that. Actually, I do have ethanol.
Okay.
But it's denatured. Okay. Thanks, guys.
All right, I'll see you later.
Ladies and gentlemen.
Wait, so did you not record here?
No, because they were able to bring the cameras in today, like this period. So they're helping me out big time. All right, just have a seat. We'll get started. Welcome. Now it's going to be weird because there's cameras. So today's lesson follows up yesterday with intermolecular forces, but we're going to apply it now to the state of matter known as liquids. What I hope you'll get by the end of the lesson is, again, following up from yesterday, being able to look at the molecular structure, see what intermolecular forces are present and their relative strength, but then to apply that to the properties we're going to talk about. So here are the properties of liquids in general, and then the specific types of properties. I think once we define them, you'll understand how the IMFs tie in. So really, IMF and temperature is what we're going to look at, and how the two affect the properties that we're discussing. So the idea of a liquid is the fact that you have molecules that are attracting each other, but they're also in motion. So it's this battle between their movement and their attractions. And in the liquid state, we're kind of somewhere in the middle, right? Because it's condensed, meaning that the molecules are stuck, but they're free enough to move around each other. So the liquid is fluid, it can flow, take the shape of its container. But it's not completely free because it stays condensed. So again, the intermolecular forces that we talked about yesterday are responsible for holding the substance in the liquid state. This is just like, junior high definition of liquid, right?
It keeps its volume, but takes the shape of its container.
But here are the properties that we want to talk about today. So I'm going to just list them first and then go through a series of slides and demonstrations to kind of cover each one. Just write the list so you have a kind of a table of contents of the things we talk about. Don't write the thing next to it. Those are the demonstrations I'm reminding myself to do for each one. So one of the properties we're going to study is vapor pressure. What does that mean? We'll see how it's influenced by IMF. That's connected to boiling point. Don't trip. Make that face right into the camera.
Yeah. Yeah, it's pretty good.
That doesn't even make sense.
2 is good.
How much is it?
It's 2 for a small, 3 for a large.
Sophia, you're interrupting the class's lesson now. Look at you. Now they're
Hi, Mia.
Hi, Mia.
Hi.
This is because all the people who are absent today for the concert.
Oh.
I thought I'd make the lesson and then they could watch it.
I will.
Yes.
I was at the concert, but I'm here.
Did you hear that?
Me too.
Okay. Another property we're going to look at is surface tension. That's going to be a little game that you guys can play as a class to see if you can get an extra 5 points today.
Oh my god. Oh my god.
Where's Alex?
He's
He
getting
went to somewhere.
I want a mountain.
So, viscosity and capillary action. So these properties, each of them, I'm going to, like I said, define and demonstrate and ask you each time, how does the intermolecular force influence this? How does the temperature influence it? And the main thing, I think you'll understand everything just fine, is can you make the arguments well enough? And do you say the right words the right way to make the explanations solid? And then finally, solubility. We've talked about solubility in the past with solubility rules back in Unit 2 with aqueous reacts with aqueous solution. But now we want to understand what is at work in determining solubility, what mixes with what and why. And again, this ties to the intermolecular forces. So, here we go. Well, just the list. just this list. You don't have to write the words next to it. Those demos are just for me.
Oh, alright.
That's just Nick's.
All right, so while we're getting ready, I need a volunteer who's going to let me smear chemicals on their hand.
No.
Me.
Anyone? Okay. So,
Should I come up?
do you want to be on camera?
Yeah.
Okay.
All
All right, I will now dump chemicals on a child. So, I want, not in this, not in
Are you
this
gonna
state.
play in class for that?
Okay.
Why would we waste all?
Any dumb thing I do now is on video, I'm in trouble. All right, I'm gonna take some liquid, I'm gonna just rub it on your hand, ready? Tell me what it feels like.
Cold.
Now, this is sitting at room temp,
Feels kind of wet, probably.
feels cold? Well, let me ask you something.
Probably like the liquid
It's evaporating.
that's evaporating into a solid.
It's gone, right?
There you go.
Fast, and it feels cold. Does this remind you of anything you feel in your every?
polish remover.
Exactly.
Oh,
That's,
wow.
that's what this is. This is acetone. Okay?
Can I go sit?
Yes, please.
Why are there two cameras? Did you
All the angles.
I'm doing it in 3D.
Which angle will they watch?
Anyway, acetone is a solvent that dissolves plastics and paints and stuff like that, and so use it in nail polish remover. But that cold feeling you get is not based on the fact that it's cold, it's based on the fact that it evaporates. So when we talk about evaporation, okay, let's think about what that means. Well, what does it mean? What do you think evaporation means?
Vaporization.
Tell me what that means. That's just another word.
Turning into gas.
Okay, liquid converting to gas. Pretty much at any temperature we can call it evaporation. When it's boiling we call it vaporization. But for the most part, conversion of liquid to gas. Now, my question is, if we looked at evaporation as a process, what's actually happening? Molecules that attract each other are moving up fast enough to escape, right? They're breaking free from the liquid. So let's ask, how would IMF forces affect evaporation, and how would temperature affect it? I want you to give me a relationship between the two in terms of how fast or how readily evaporation happens. Yeah. Okay.
So IMF, the stronger the bonds, the harder it would be to evaporate.
So the stronger the bonds, the
More time it would take.
so like the less evaporation.
Yeah.
You're saying something like that. So stronger IMF. You're saying slower, less evaporation. Do we agree?
Because like water takes a long time to evaporate because it has hydrogen.
That's very good. Now, how would temperature affect evaporation? I'll say higher temperature, you tell me what you think happens. So faster evaporation. And do we all understand that's simply because the molecules, when they're moving faster, there's going to be a higher proportion of them with enough energy to escape. Now, I'm just going to remind you that when we heat a material, if we start at one temperature, there's a distribution of energies that looks like this. And let's say this is the critical energy. Let's say this is where the energy is needed to evaporate, right? So only this many molecules have enough energy to escape. When we heat it, this curve shifts. Do you remember these Maxwell-Boltzmann distributions? And now what happens is a much larger proportion of molecules will have the energy to escape. And so we should expect evaporation to happen faster. That's our experience. Where do we see evaporation in a cooling sense?
Sweat.
Yeah. So here's a good piece of advice for those of you who care. If you want your best stats, always first thing in the morning. When you're sleeping for 8 hours and not drinking water, you're evaporating water all the time. Your body's part of its system to cool it is evaporating water. You're not dripping sweat, but you are sweating. So you're going to always weigh the least in the morning. And you're also going to be your tallest. Because when you're laying flat for 8 hours, your body extrudes. Versus when you're standing and sitting all day, gravity compresses your spine. So you're lightest and tallest in the morning.
That's so easy.
Okay,
Just don't eat anything.
right.
What
So
a
we just
great-
said all this. I don't think I need to say it anymore. Let's jump ahead. So now I'm going to define something. There's too many words. Let's get rid of the words. Now I'm going to define something called vapor pressure. Okay? So, if we have an open container of water. So let's say I take a flask and I fill it with water. What does that water do over time?
Evaporates.
It evaporates. So evaporation, as we just said, means that water molecules are going to go in the space above. And if the container is open, they're going to escape, right? And eventually, if we wait long enough, won't all the water simply go away? Right. But at a given temperature, what happens if we stopper the flask? The water is evaporating, and so it's going into the space above the liquid, and we're getting the vapor up here.
It's gonna condense.
It's also going to condense, and eventually, what will happen to these rates?
Equalize.
They will equalize. And when they equalize, the amount of vapor in this container will stay constant.
Can you put those in words?
Sorry. This says, let me write it better. So this one is evaporation, and the other one is condensation.
Is vapor pressure under evaporation, or is that another?
It's related to it, that's why, yeah, it's still connected. But so when those become equal, we reach a state of equilibrium, meaning that the amount of vapor and liquid no longer change. And so now if we connected like a pressure gauge inside here, this vapor, like any other gas, would exert pressure. And so we can define that as the vapor pressure. Well, what does that actually mean? Well, it's literally the pressure exerted by a vapor in equilibrium with its liquid. And so this picture is supposed to illustrate what those words are saying. Now, it is connected to what we just said about evaporation. But if I tested different liquids at different temperatures in this container, they would have different intermolecular forces, and we could test different temperatures. So just like we did a minute ago with evaporation, if I asked you to tell me how do these affect vapor pressure, what would you tell me? Like, how would you explain the effect of intermolecular force on the vapor pressure versus temperature on the effect of the vapor pressure? So if the intermolecular force is high or strong, what does that do to the vapor pressure? The vapor pressure would be lower because it's harder for it to evaporate, so there's less vapor exerting pressure. Does that make sense? What about if the temperature is high? What happens to the vapor pressure? It is higher because more molecules have the ability to evaporate, and there's more vapor in the container, and it's hotter for that matter. So what is vapor pressure really measuring? It's really measuring the tendency of the liquid to evaporate, how easily it evaporates. Let's see what this looks like in real life. So I'm going to do a demonstration that I affectionately call gasping flasks. So in one I'm going to put acetone, and the other one I'm going to put water. Where did I put my acetone? Oh yeah, I just rubbed it on you. So as I add the liquid to the container, there's still some left over from earlier.
Was that acetone?
Yes.
Won't that get stuck in your nose? Won't that get stuck in your nose?
I won't get stuck, but it doesn't feel so good. So I'm going to pour a bunch of acetone in here, and then I'm going to seal it. And once I seal it, it's evaporating, but the vapor can't escape. If I leave it open, it'll all disappear over time. But what's happening now, it's evaporating into the space here, and just to kind of give it a little help, I'm going to shake it up with it.
Why would that help?
And just give a little more energy to the system and help some of it evaporate a little bit more readily. So I'm going to let that sit there for a minute. And then on the other one, I'm just going to add water. What are you talking about? I'm trying to keep the amounts pretty similar. Okay. And this one I'm also going to kind of shake up, just so I'm treating them both fairly.
Which one's water? Oh, wait, no.
The one that says water, it used to say water. All right, now, we can imagine this is happening in both containers, but one of them is water with this molecular structure, and And one of them is acetone with this molecular structure. So here's the key to answering these kind of questions. First, we address what intermolecular forces are present. Second, we assess which are overall stronger. And third, we apply it to the property in question. So here's the thing I want you to do. First, tell me what IMFs do each of these have? What does water have? So,
IMF.
dispersion,
Or yeah, dispersion.
dip,
And
and hydrogen bonding. What does acetone have?
Dispersion.
Dispersion, dip,
That's it.
and that's it. Now we have to be careful. This is not just a yes or no situation. Because dispersion, just because they both have it doesn't mean they have equal dispersion. Doesn't this have more dispersion since it's a larger molecule with more electrons? And the dips may have varying strength as well. But certainly hydrogen bonding seems to be the big factor here. And as a result, which of these would we expect to have the overall stronger intermolecular force? So if we chose this and said this has the overall stronger IMFs, what would we expect in terms of their vapor pressures? Who would have the higher vapor pressure?
The right side.
So the acetone, we would expect to have the higher vapor pressure, and the water, the lower vapor pressure. And this is, of course, assuming the same temperature which they're at. Question?
What is it when you define vapor pressure? What do you mean by like in equilibrium with this liquid?
So right now, these two are liquids, right?
Yeah.
But above the liquids, some of the liquid has evaporated to become a vapor, right? So in equilibrium means that once, because I've closed the container, the vapor can't escape. Enough vapor forms up here so that it's condensing as fast as it's evaporating. Now the amount of vapor stays constant.
Okay.
Equilibrium. So there's no more net change. Right? So now here's how I'm going to prove which one has a lower vapor pressure. We're going to do the gasp test. So I don't know if they'll be able to hear it on the camera, but it's kind of subtle. So I'm going to just open the stopper and you listen for what happens. Ready? Nothing, right? Okay. That's the one with the lower vapor pressure, the water. Now if this has higher vapor pressure, we might hear something more. Ready? Did you hear the?
No, I heard your stopper.
Yeah.
You didn't hear the?
No.
I heard stopper.
No, the stopper was too loud. It went.
Oh.
Or maybe I can do it again if I do it like this. I'll just hold my hand over it.
Ew.
Right? Did you hear it go?
No.
It's too soft now because it's full of vapor and I can't make a big difference anymore. Because now it's loaded. Now you screwed me up.
We did that.
Here, I'll do it one more time.
Nick is dead.
Ready? There, did you hear that one? Okay, good. Whatever, so what? I failed. All right, well that didn't work so good. That's okay. You get the theory, very good. Now, what's interesting about this, because I'm going to skip a bunch of pages, is this next graphic where we see a combination of different substances on a graph of temperature versus vapor pressure. How would you say they are related? How are vapor pressure and temperature related?
Directly.
Disagree.
Exponential.
It looks more exponential.
That looks very linear to me.
That was Sophia.
Trivia.
Mr. O'Bricky, she thinks these are linear.
Biochem.
Okay, anyway. So,
Dentist.
I got that on. All right, so what the main thing is, as it gets hotter, the vapor pressure increases. Now, you'll also notice we marked the specific vapor pressure that is standard atmospheric pressure in torr, and that we connect this somehow to the boiling points. But what's interesting is that not all the liquids increase the same. How do you account for this? Why is diethyl ether here, although it's increasing, but ethylene glycol is still way down here? What's the difference between the substances, do you think?
Bonds.
Why? Like, what would you say about the bonds? The intermolecular forces, let's be specific.
The stronger it is, the lower.
So which one do you think has the strongest intermolecular forces?
Ethylene glycol.
Right, and this is used in like cars as the radiator fluid. So it lowers the freezing point, but it also raises the boiling point because it's harder to turn this into vapor. So instead of like using water, where it could boil over and blow the radiator cap and steam, this can absorb more heat before it does that. So that's why it's used. But something like diethyl ether has a very high vapor pressure because it has a very low IMS. Yeah.
Do you only look at do you only compare molar mass if it's like one thing changing?
No, because here, if you compare, this one would be just slightly polar, so pretty weak IMF
Like, do you
overall.
look at bonds first, and then if you
Oh, I
can't
see.
figure out the bond, then you look at molar mass?
Well, the molar mass only influences the bonding indirectly because higher molar mass implies more electrons, which implies higher dispersion because it's more polarizable. So it really is connected to the bonds indirectly. But here I mainly wanted to show you that how the vapor pressure is connected to the temperature and to the intermolecular forces again. Now, what's interesting is the boiling point. Most of you don't really know what boiling point means, so I'm going to tell you now. And then I'm going to come back to this graph. So, what do you think boiling point means?
The point of something boil.
Very good, Nick.
Liquid to gas.
What kind of measurement is it? Yeah, for example, what are we measuring? No, that's incorrect.
Celsius.
Okay.
Kelvin.
Temperature. Can you just say the word temperature? Boiling points are temperatures. So a boiling point actually is not quite what you think. I'm going to put the definition up and then see if this connects to things you're used to. This I'm going to actually project it. Here's what boiling point actually means. It's the temperature at which the vapor pressure of a liquid is equal to the external pressure. Now what the heck does that mean? It means a couple things. It means that, if I'm understanding this correctly, since liquid vapor pressures can change and external pressures can change, doesn't this sound like a substance can have more than one boiling point?
Oh yeah.
Like it doesn't always boil at the same temperature. I've been telling you this kind of all year when we used boiling water in our experiments to not assume it's 100, but to measure it with your thermometer, because it can vary. But why? Well, it's also tied to the fact that if you have a pressure cooker at home, you use that to get hotter temperatures and faster cooking times in the water. Or if you ever look at rice or other pastas, or even eggs, really, if you cook them in the mountains, it takes longer than if you cook them at sea level.
Is that why like you can boil water faster if you put salt?
No,
Or like that trick?
no,
Salt
that's
breaks
different. That's different. But we're not talking about the speed of
Whatever.
boiling.
Disregard that. What I just said.
Please have that stricken from the record.
Redacted.
Redacted?
Yeah.
How do I redact it? I draw a line. Anyway, my point being, it's not about the speed at which it boils, it's the temperature at which it boils. Because once it reaches boiling, it stops raising in temperature. But check this out. I want to show you why this works and what it means. What do you most associate with a boiling liquid? What makes you know it's boiling?
It's
Bubbles.
makes bubbles.
The bubbles, the bubbles. I'm going to say no to the speed and you'll see why in a minute. So, when you have a liquid, and you start to heat it,
Oh yeah, I was asleep.
its vapor pressure,
Sorry.
raises like we saw in that graph. But what's stopping it from bubbling initially is the external pressure, usually from the atmosphere. So the fact that there's air pressure pressing on the liquid is compressing the liquid with that same pressure. Now that pressure can vary, but at standard atmospheric pressure, 1 atmosphere, we call the boiling point the normal boiling point, the one you're used to, like water's 100. But what happens if the external pressure decreases? Well, consider this. I'm going to be specific and use water here because I want to make a very particular point. When you see water boiling, you see bubbles form inside the liquid. What's in that bubble?
Air.
Air,
Gas.
That's wrong.
fire.
That's wrong.
Wait, H2O in its gas form.
Yes. In other words, water vapor.
Oh. Oh, condensation. Gas.
No, that's the opposite of vapor. This is the vapor inside here. Now think about this. If you try to open up a vapor bubble, what does it have to push out of its way?
Water.
The liquid. But isn't the pressure squeezing the liquid and making it harder to open up a bubble?
Yeah, probably.
So when the vapor pressure of the liquid has reached the outside pressure, that's when we have enough force for the bubbles to open.
That is pretty interesting.
It is not only incredible, it is why we associate boiling with heat. Because what's the only liquid we regularly see boiling? Water. And water, we heat to boil it on the stovetop, for example, and it's really hot. And we see the bubbling, and we even think of the word boiling as another word for hot. But I'm going to show you that I can boil water without hottening.
What?
This is water.
Oh, you're probably
Do you
just
feel
gonna
how that feels?
push air into it and
Ah.
fake it.
Oh,
You're gonna fake it.
it doesn't work.
Huh? Your mouth?
Yeah. All right, I'm going to put this up here, and there is a small chance that it could explode, well, implode really. Those are marble chips or boiling chips. They're meant to kind of make the bubbles not as violent, and so it breaks the surface tension, so the bubbles are kind of smaller.
It's Alka-Seltzer. It's gonna start heating it right now.
That doesn't make any sense. Okay, I shall now turn the pump so you can see that the pressure will decrease, and with any luck, not destroy the containment system. We shall now boil the water. Boil!
Oh, wow.
It's bubbling, it's boiling. Boiling is hot. The water must be hot because it's boiling.
That's funny.
Gotta be really careful now because it's boiling water.
No, it's
There, you heard it.
chips. It's because of the chips.
Look at steam. It's boiling hot.
So weird.
What? It's boiling.
It's not.
Not at all. It's the same exact temperature.
What? That's not possible. That's magical.
What happened here was, instead of me heating water to meet the vapor pressure of the outside pressure, I brought the pressure outside down to where water's vapor pressure already is. So I got the pressure down to, let's say, 10 or 15 torr, and the water's already at that vapor pressure at room temperature, so it boiled. And so that's what you saw as the boiling effect. So what I'm showing you is that this tells us that water can boil at a lot of different temperatures. It depends on the outside pressure. So if you're up in the mountains where the atmospheric pressure is lower, the water is boiling, but it's colder, and it doesn't cook the food as fast.
All of that. Or it doesn't cook it at all. Because it's cold water.
It could. Like this would never cook anything.
Yeah.
All right. So, just to make it clear, when I say boiling point, I normally mean the normal boiling point. When the atmospheric pressure, standard atmospheric pressure, equals the vapor pressure of the liquid. So that's why when we say water boils at 100, we're tying that specifically to standard atmospheric pressure being the vapor pressure. Okay? Alrighty then. Moving it along. The next thing we're going to look at.
Don't change it. Wait.
Wait.
It's a very interesting accent. Oh, normal one.
I'm doing this so they think the camera froze.
You just told them you're doing. Anyways, you just told them that you're gonna do it, and then you did it. So then they're gonna know that it wasn't frozen. Let's go.
It's turning colors. Okay. Maybe it'll put foot later. Moving on.
Why is it purple?
Yeah, why they actually?
See, I told you put stuff in.
Yeah, why they turn?
That's a different container. See?
Wait, why they turn purple?
I think some of the ink, I must have gotten some ink in there, like from the marker.
Dang.
All right. You don't need that. All right. Next one. This is going to be a little challenge to the class. So surface tension has to do with the fact that if you're inside the body of a liquid, the intermolecular forces are acting on me in all directions. But if I'm at the surface of the liquid, then outside of that surface, there's no other molecules of liquid to attract me. So what happens is I'm attracted inward and sideways, but not out from the surface. And as a result, the liquid kind of pulls itself together, and that's why that common effect of seeing, like, say, little like balls of liquid on a car or something, or on a surface where the water doesn't wet.
A dome.
Like a little dome. Thank
Yeah,
you.
dome.
A dome.
A bead.
A bead. That's a good word.
A marble.
Got it. Anyway, it should be evident that the surface tension, which measures this kind of tendency to bundle up at the surface and kind of hold its surface intact, is going to be connected to the strength of the intermolecular forces. Now, does it make sense that when the intermolecular forces are stronger, it holds together better?
Yes.
And therefore, the ability to kind of spread the liquid apart becomes harder. If you've ever belly flopped in water, you know what that feels like. So this is just showing it kind of at different levels. The relative surface tension compared to the attraction to a surface determines how round the bead is. So if the surface tension is high, in other words, if the molecules attract each other very strongly, they tend to ball up. But if they attract the surface they're on more strongly, they tend to spread over it. And so I'm kind of showing that in a molecular level picture here.
Is there an example for the left hand besides water?
Well, we're going to look at any number of liquids. Every liquid can be attributed to surface tension. I'm just using water as kind of the model that you're used to. And I'm going to use it for my demonstration. So we all know that steel is more dense than water, like 8 times more dense. But if I'm careful, and you've probably seen something like this before, but I'm going to do a twist on this. I could float a paper clip on the water. So I'm going to grab the clip, and this is where I'm going to challenge you guys. So everyone can actually see what happens. See how it's floating on there?
Well, I don't know if you see it.
Look at how the paper clip is floating.
You need a bird's eye view.
It's gonna burn. Here, you want me to get the camera? I can
No.
point it right.
All right, while I'm getting ready for my next demonstration, so you can see how the actual surface looks like a skin bending around the paper clip,
Yeah, we saw.
I'm going to give you this, and look at it, don't let the paper clip fall. If it gets all the way around the room and everybody hands it off, 5 points.
Oh, shoot!
Sophia, you're gonna be the one that's.
I know.
Can we get more than one chance?
Yeah.
Gosh.
That's just not how life works, Nick.
Okay, it doesn't have to do that.
Just go really slow.
Just don't tilt it or shake it.
Wow.
Get up, use your legs.
We don't have all day. The other class figured out the best way to do this. See if you guys-
Everyone's
Guys,
closer.
everybody just stand up and
What if I
fight.
put it on the desk?
It'll probably make it fall.
Let's just
All
all.
Wait, we can
I
move,
wish
right?
the people on the camera could see this.
We can move, right?
You can move. I didn't say you couldn't. Just don't trip over the camera. You have to pass it though. You can't just all touch it.
Anna, you can't! Stop!
Give me it.
Stop! Careful!
Tell me when you failed so I can laugh.
I bet it's not gonna even fall. We're just looking like idiots right now.
Stop! Stop, Nick! Stop, Nick!
Don't bump the camera. Oh!
Yeah, it's not gonna fall.
For those of you watching at home,
Don't give it to Zoe.
they look like a bunch of fools passing a beaker of water around. And they're all yelling at each other. Oh, and they just kicked the camera.
Hey!
Okay, that was Nick's nose. And he just kicked it again.
One day I'm just gonna beat Nick up.
All right, that's on video. Thank you.
Why is your
That was
tripod from
Sophia
Miles
elbow
West?
dropping Nick. What?
Why is your tripod from Miles West?
People over there need to come over here.
Wait, is it actually gonna break? Do you feel like too much?
Yes.
I think you give it to me.
Swear, that's not helping us.
Sorry.
Oh, it's really show. Oh, he can see
I have it this way so I can see what I'm doing.
No, I didn't touch it.
Where is it?
Sophia's too short for the
Are we getting there?
Renegade.
Alex. 2 hands. Two hands.
2 hands. 2 hands on the sippy
All right, now I'm going to mess you up. My Hulk smash isn't working.
Hi, Mia.
Wow. That's awesome. That's
Did that just happen? Wait, how did
just had a minor earthquake.
The other one's
I think that's it.
We got it!
I don't believe you.
We did it!
That's such a lie.
We can do it again.
I bet like it's so hard to make it fall.
I think I saw every single.
It's so hard to make it fall.
mess up at any point.
Did anybody even look at how it actually looks?
No, it's not that important.
Wait, so we're getting the 5 points?
Yeah, it's like
You
bend.
see how the water seems to bend around? It's because the liquid.
No, I won't.
Did we
I
get it?
told you. I bet
Can I
it.
make it fall?
Did we get it?
Wait, did we get the point? Did we get
Did
the
we get it?
Yeah.
I'll tell you after you make it fall.
No.
Keep pushing. Oh wow.
That
It
was
sank right away. So again, the point is, it was being held by the sideways attractions to the water, or the surface tension. Now, why is the surface tension going to depend on the strength of the intermolecular forces? Because the stronger the attractions, the harder it is to push the liquid molecules away from each other and get through the surface. Okay? All right, next topic, viscosity. Viscosity is not thickness. Viscosity is not density. Viscosity is resistance to flow. So when you think of something like syrup, it oozes when you pour it. That's what I mean by viscosity. So it should make sense
Very
that if the intermolecular forces are higher, the viscosity should be
Higher.
It's
harder to
Can you
flow.
repeat?
the higher the intermolecular forces, the higher the viscosity, meaning the less it flows. Does that make sense? Because if the molecules stick to each other very strongly, they can't move around each other as easily. So things with higher intermolecular forces should typically have higher viscosity.
So why does water flow
Yeah, I was
if
gonna
it has a
ask
super
that.
high intermolecular force?
Because another factor is that the total intermolecular force is high in some ways, but the molecules are very small. Did you ever stir like long strands of spaghetti or even like comb your hair if you have long hair and it gets all tangled up and hard to get through?
Yeah.
So in a similar way, if you have long chain molecules, their ability to kind of intertwine and have multiple points of attraction also makes it harder for them to flow. That's why things that are nonpolar, like motor oils, can be very viscous, because they have large chain molecules with, even though it's just dispersion, there's a lot of points of contact.
So larger is also more viscous?
Yes.
Hydrocarbon.
That's right. Furthermore, how does the temperature affect viscosity, do you think?
Since they're moving
Yeah.
higher means
Like when you heat up peanut butter, it gets like runny, so.
Yes. I was thinking most people heat up something like syrup.
When I make
Lucumadas, exactly. Boom. Greek
raisin
connection.
toast, I put peanut butter and Nutella on it.
I think we end this conversation.
Every time, I know.
And then you melt this together.
Okay.
It's really good.
So wait, let me take a pause here. Is it evident what I said? Hey, you're making me hungry. This is a peanut-free room. Is it evident what I said, that this is making sense?
Yep.
Like once you know what the property is, how to connect the,
Yeah.
right? I mean it is, isn't it? So let me ask you this. I'm going to test viscosity the following way, but I want you to predict it before we actually test it. So here's the test. Which of these molecular structures do you predict would be the most viscous? So one of them is going to be acetone again, with this structure. One of them is going to be, this is acetone. One of them will be water. And the last one is going to be glycerin, which has this molecular structure.
are they all around the same?
Well, that's what I was going to show you. In some ways, yes, in some ways, no. Consider these structures, okay, because there's kind of competing effects. So first, let's look. If I said rank them according to their viscosity based on the structures, first you look at IMFs. Let's just list IMFs in this one. Dispersion and dipole-dipole. In this one,
All of them.
dispersion, dip, and H. In this one,
All of them.
So again, I'm picking examples that I hope are illustrating the fact that it's not just is it there or not, but you have to look at the whole picture. In other words, this only hydrogen bonds in a little space. This has 3 different positions where it can hydrogen bond. Do you see what I'm getting at?
Yeah. So that's probably like very viscous.
Okay, let's see. And then which one would you expect to be second and third?
Acetone second and third.
No.
Hydrogen.
Wait, what?
It's
H2O
bigger.
second.
I think that's debatable and that it's not
No.
necessarily obvious, but the hydrogen bonding might be the bigger effect, but the molecule is small. But like you said, this has more dispersion because it's larger and it's maybe more entangleable.
I said there were more.
So which is right?
Let's find out. So let's start with the obvious one. You guys said that glycerin should be the most viscous, right? So let's see what that looks like. Here is
It's like honey.
here's glycerin. So there's a little marble at the top. There goes an air bubble.
Oh.
So instead of me pouring it, I'm just letting this object fall in it. Can you see that it's actually falling?
Yeah.
The little white marble is very slowly moving.
Oh, it's the marble.
At the top?
Yeah, there's a white marble at the top falling down.
Oh, so
You
there's
found the air
Well, either one, even the air bubble, you can see how slow the air bubble goes through it.
Where's the marble?
That little white thing?
right there.
Isn't that an
They're
air?
meeting.
No, the one going up is air. That white thing
The
is.
one going down.
moving down.
You don't see the white thing there?
What?
You don't see the white ball?
Oh yeah, take off your glasses.
I mean, like, Kiwi, move it. Kiwi's like, oh, wait. I think it was the light.
Oh, okay. How's that?
No, that was worse. Go back.
All right. Now the other two might be harder. Let's see. Here's acetone,
The white stuff.
No.
and here's water. All right. Here goes the water. So you see how fast that's moving?
Oh, well, that's so weird.
It's not very viscous.
Okay. And now here's the acetone.
Ah, shit, I got it wrong.
Oh, the acetone is faster.
Why is it so fast?
Can you tell? We can race them. Ready? Go.
Okay, that looked like simultaneous. Oh, never mind. On the way down, you can see.
But this kind of gets to the point that it's not as obvious, right? It's not a clear. I mean, you can tell, but it's not like one's that much more than the other by this appearance. So there is some competition between the fact that one has the stronger type of bonding, but one is larger.
Is that just this example in general, or always look at bonding first?
I would say usually you're going to be asked comparable things. If you're asked to rank them, they're going to be comparable. If they're not, they're going to tell you the answer and say, explain it.
Oh, okay.
So if they said this one is more viscous, then you would say, oh, it must be because it has the stronger intermolecular forces.
What's the other one?
But if it had like a long chain hydrocarbon and said it was more viscous, you'd say even though this only has dispersion, it's so much larger, the dispersion is stronger. And so you can make the right argument. Yeah.
So you like a little recap of that, like, okay, this is like high molecular force, and then
Me?
like boiling point is like high molecular.
Yeah, we were going to do that with the lab activity part. So it's all going to recap again. All right, moving on then.
Are we gonna do a lab report on
We have a lab?
No, I'm going to do it like a demo lab. I don't think much. It might a little bit because there's stuff dissolved.
Wait, so we got the 5 points, right?
All right, moving on. No, it's just a paper. You'll see.
It's your face.
If you guys can look here, when this morning, because this takes a long time, I took a paper towel that was dry and I shoved it in a beaker of water. It's this one, and I just put the paper towel over into this beaker, and it's been sitting like this for several hours. But what's happened is water has traveled spontaneously uphill, and on the other side, it's starting to fill this beaker. And this will continue until the water levels are equal if I leave it overnight.
Is this the capillary
Are they both water?
Yes, yes. But this didn't have anything in it originally.
Oh.
Is that
So
like how we can swallow even though we like when
No, that's
upside down?
peristyle. That's muscular.
Oh.
That's
What?
I was gonna say roots on plants.
Is that why chicken tastes so good? Yeah, Nick, that's why. Okay. Anyway, so here's the point. What's going on here is that when you have very narrow tubes or openings or spaces, the attractions from the intermolecular forces of the molecules and the surface of the material it's interacting with can cause the liquid to climb up against gravity, and that's what we call capillary action. It's evident in like root systems of plants, which have really fine hair-like root structures that can help kind of draw the water in and rise it up. But it's really based on the difference between what we call the cohesive attraction or force which means molecules attracting similar molecules, so water to water, versus an adhesive force, which is how well it sticks or attracts to some other substance or surface. So water sticking to glass, for example. And so when you have very strong adhesion, meaning attraction between the liquid and the surface, it's going to tend to climb up the surface higher. But the thickness of the tube also makes a difference. So I've taken the liberty of taking 3 different pieces of tubing of different diameter, they're all the same glass, just so I can demonstrate the effect of how the thickness of the tube matters. And this is water that I've added watercoloring, food coloring to, just so that you can see it better. So I'm just going to dip these in, and then I'm going to pull it out and see if the water climbs the tube at all. And if it does, it's because it sticks to the glass. If it doesn't stick to the glass, what would happen? It would just fall right out, right? What's holding it in is its attraction or adhesion. So let's see how that works when I dip it in, right? They're all at the same depth now. But when I pull them out, the heights of the liquid are different.
Why?
Wait, how did they just stay there? They just-
So, adhesion, but there's another principle at work here. Why isn't it just falling out? Isn't the air just going in? Very good. The water has a strong surface tension, and that keeps it. But do you see the differences in the height?
Yes. Yeah, kind of. You guys are so smart, right?
Okay? Now, the thinner I make the tube, the taller it can climb. And the reason for this is basically what's carrying the middle molecules up is attaching to the other molecules next to them. But the only ones that actually have something to stick to climb are the ones at the surface by the glass. So the thinner the glass is, the thinner the tubing, the more of it is literally on the glass. And so it can climb higher because it's not lifting as much weight of the molecules in between. Yeah.
Is this video gonna go on your site?
Yeah, I'm going to link it there.
Wait.
Watch it.
I'll watch it.
Yeah.
I'll watch it.
Is when you're talking about capillary action, are you comparing like adhesive to cohesive? Like adhesive, the adhesive force is larger than the cohesive force.
Yes.
So in that case, it is.
In this case, it is, and this is adding the extra comparison of the fact that the thinner the tube, the higher it can climb. But if I was to dip this, let's say, into a very non-polar liquid, like let's say here, I'll do this. So although it's not colored, I don't know how easy. Don't trip over it. So let's dip it. Let's dip it into acetone and see. Actually, I can just to see. I don't know how visible this will be. Yeah.
Cohesive forces like intermolecular.
Yeah, these are just the forces we're referring to, the intermolecular.
Same thing.
Yeah, but it's just which is it. We call it cohesion when it's molecules attracting each other of the same kind. We call it adhesion when they're attracting to other molecules. Yeah.
All the same amount. Like they all take the same amount of water.
Oh, you mean is the actual volume of water the same in each case? I believe that's right.
Oh.
Now,
Oh.
here is acetone, which has a much lower adhesion to water. So when I know I didn't color this one, but when I dip it in now,
Oh, I see.
it climbs this one a little bit. It climbs this one. This one I can barely keep it even in the tube. But it's lower overall because the attraction to the glass is weaker. So I'm sorry I don't know if I could get this to show the color, but the climbing is much less.
So do you compare adhesive forces to other substances, or just in general? Like, is it relative to one another? Like
It is.
Okay.
But that's again going back to the idea of intermolecular forces. And so to kind of tie this to another aspect, if you look at meniscuses,
Whoa.
if you take mercury, which is a nonpolar liquid, notice that it makes an inverted or convex meniscus. What does this mean? It means that the mercury bonds to itself, meaning higher cohesion, and it doesn't bond well to the glass. So you see how it avoids the glass and bunches up in the middle? That's showing that cohesion is beating adhesion. In other words, it does not stick to the glass well, so it does not really climb. It avoids the glass.
cohesion.
So here, cohesion wins. But what kind of meniscuses are we used to seeing?
Water.
Right.
Concave down.
And it turns out that glass is a very polar surface and water is a very polar molecule. So when you look at what's going on in the water, in terms of capillary action and formation of meniscus, the water climbs up at the sides and bows down in the middle. And you also have noticed that this is more pronounced when you use a smaller graduated cylinder, right, when it's thinner.
Yeah.
And that's because, again, that action of the thinner the tube, the more the effect. But this is showing that the water molecules can attract very strongly to the glass surface, and there's stronger adhesion. So here the adhesion is kind of winning in a sense, because the molecules are actually sticking better to the glass than to themselves, and so they start to climb at the edges where they
Are
can.
there any where it's perfectly flat? Because
I don't know of any offhand, but
That would be so weird.
I would imagine that things that have very low surface tension and very weak intermolecular forces in general would tend to basically flatten out. Yeah.
That's an indirect relationship
In which way?
between cohesive and adhesion. So as cohesion increases, adhesion will decrease.
I think that's a fair statement. I wouldn't quite call it a relationship because, but yeah, I think I'd say that's fair. All right, last one, and then we'll do the lab version of this. So we'll, like we said, like Zohair said, we'll recap our, and then you guys just write up this lab.
Oh, we do have a lab.
No, I'm gonna. It's a demonstration on a paper. It's simple. All right. So this last demonstration is actually really interesting because I think it'll trick your mind a little bit. Number one, when we talk about solubility, the term we usually use is like dissolves like. That means materials of similar polarity mix well. But why? Why should things that are polar like other things that are polar? And why should things that are nonpolar mix better with things that are nonpolar? And why should polar and nonpolar not mix well? What's actually going on? Well, if you're guessing it has to do with intermolecular forces, you are correct. But what? Well, let's start by asking this question. What has to happen for two things to mix? On a molecular level, what has to happen for one thing to dissolve in another?
To break down.
Yeah, so you have to move the solvent particles apart, you have to move the solute apart, and then you have to mix them to each other, right? But that means we have to fight against their attractions, and then we get some attraction back when they mix. So what determines how well they mix is how well they bond afterwards, you know what I'm saying? So think of it this way.
Wait, go back for a second.
I know, like, literally.
Sorry.
Okay, that's good.
No, it's not. No.
That was it?
Yeah, and I was.
Wait, no, really? I'm good. So, anyway, my point being that even solubility is based on attractions and intermolecular forces. Ultimately, and you don't have to write all this down, I just want to make sure it made sense what I said because I put it in a chart form for you. There's an energy involved in expanding the solute, meaning pulling apart the particles. There's an energy involved in expanding the solvent, moving them apart. These both require energy.
Yeah.
But then we hopefully get energy back when the solute and solvent attract. Now, if this costs more than this gives back, they're not going to mix well. But if this gives back similar or more than it costs, then they will mix well. That's why things of similar polarity, we're interrupting certain bonds, but we're getting back about the same bonding. But with nonpolar and polar, when you interrupt the polar bonds, you don't get as much back when they try to attract to nonpolar molecules. So to make this a little bit more clear, I'm going to make an interesting mixture. Now this is going to trick you at first, but I'm doing this on purpose because this is not just yes or no. There's a little blur to our idea here. So I'm going to start by mixing two substances, one of which is hexane. So here's hexane. So it's just a long hydrocarbon chain, straight chain of carbons and hydrogens. The other one is ethanol, which in some ways looks similar, but it has an OH group on the end. So in fact, to make this more clear, let me write this another way. It would be CH3, CH2, 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 1, 2, 3, 4, 5, 6. Okay?
Problem set.
It's pretty close.
Now, when I compare these two, can you tell me what kinds of intermolecular forces they have?
That one has dispersion.
Just dispersion.
Oh,
This one?
hydrogen?
And then is there H bond?
Hydrogen.
Has all three.
Oh.
Now, we might predict, because this has polarity and this does not, that they shouldn't very well mix. But doesn't this also have kind of a non-polar part?
Yeah.
So that kind of makes things blurry. Now check this out, because this really gets to the heart of the blur and how to understand it. So I'm going to take some of the hexane. This does not smell good, by the way, so you might start to notice that.
What is he trying to prove?
That what mixes well and what doesn't mix well. So this one is hexane. By the way, look at how it shakes. What do you notice about its
Not
surface
viscous,
tension and
not
viscosity?
Not viscous.
Low surface
You see how that shakes? And remember how you asked me if it's
It's
flat?
straight.
You see how flat that is?
Yeah.
Wait, viscous means like it's like thick, right?
Yeah, not thick though, but resistant to flow. Now, I'm going to take some ethanol and try to mix them. If they don't mix well, we should see layering. So I'm going to pour about an equal amount.
Are they the same color?
Yeah, but you'd still see a line between them.
It's close now.
Do you notice any separation between them?
No.
So doesn't this look like they mix pretty well?
Yes.
So this seems to go against what I said. Like dissolves like, right? Let me just stir it up a little bit and make sure. It seems to be mixed. So when two liquids mix completely, we call them miscible. That means they can mix in any proportion. If they're immiscible, that means they don't mix and they separate into layers like oil and water. So far so good. I'm going to add something else to the mixture and see if it dissolves. What do you think will happen if I add iodine into this mixture, which is basically I2?
Oh, you forced the ethanol to
Well, is the iodine polar or non-polar? What kind of forces does it have? Dispersion only. So this is non-polar. This one's polar. This one's non-polar. These we got to mix because this has kind of a non-polar component maybe. What will happen? Will the iodine dissolve in it?
the iodine is going to
No.
mix with the hexane,
Wait,
and then
is
the
it gonna like
ethanol is going to
sink
be
where the hexane
left
is?
out.
Well, it seems like the hexane and the ethanol are completely mixed though. So I'm not sure if
It's
The
not iodine.
hexane and the iodine are gonna
The
react.
polar part of
And then it's
ethanol
gonna
is
make
gonna be
it
on top.
polar, and then it's gonna react with the ethanol.
On bottom.
What?
I don't know.
Well, this is a purple solid. I'm going to drop it in. If it doesn't dissolve, it'll just sink to the bottom. Let's see if we can.
Yeah.
I know, it is. But in this mixture, we get a phenomenon called what's the word? I can't remember. Solvatochromatism or something like that, where the solvent can influence the color of the mixture. And you'll see that in a minute. But do you notice that it completely mixes?
Yeah.
So the iodine has no problem mixing with this mixture because this mixture's non-polarity seems to be kind of dominating right now. But now I'm going to throw in a spoiler. I'm now going to throw water into the mixture.
But why are these even mixing? Because doesn't that go exactly what we did down?
That's my point is, polar and non-polar is not a yes-no question. It's a question of degree. So far, this bit of polarity is not offending this non-polar molecule enough to not let them mix. The dispersive forces between them are still good enough to let them mix pretty well. And because this has dispersion, it also intermixes pretty well. But watch what happens when we add the very polar water. Do you have any predictions?
It separates the ethanol.
Like it's gonna explode.
Well, what will the water molecules tend to mix with best?
OH.
Out of all these,
I don't know.
Ethanol.
because they can hydrogen bond to each other.
Yeah.
So now it's not a question of the fact, oh, these don't mix or do mix. It's what attracts what more. Check this out. Ready?
Does density play a role in this?
It's just where the layers end up.
Okay.
So now, two things of interest have happened. You can see by how it's shaking on top that the ethanol, the hexane part went to the top. The ethanol in the water, which is a more dense mixture, sinks to the bottom. Some of the iodine stays there, but look at where most of the purple iodine ends up. It prefers the nonpolar part. So even if I try to force them together now, they will naturally reseparate, not because just it's polar or nonpolar, but what attracts to what best. So the like here, meaning the most nonpolar thing, the hexane, keeps most of the iodine with it because those interact the best.
So like.
The water and the ethanol can hydrogen bond, and so they tend to join and squeeze the other components away from each other.
Okay.
So like after you mix it, it's separated pretty quickly.
Mhm.
So why does water and oil take longer to separate?
Again, it depends on a couple things: the viscosity and how hard it is for them to move apart, and the relative forces of attraction. Actually, that's going to come up in
Yeah,
our
like
lab
a
in a minute.
salad dressing.
Is that how dish soap kind of mixes the oil?
Yes, if I add dish soap to this, the nonpolar end of the soap molecule tends to attach to the nonpolar stuff. The polar end allows it to mix into the water, and so it kind of acts as a bridge between them. That's what soap molecules are. Detergents in general are ends that are kind of like this, but have a more extensive nonpolar component and a more extensive polar component, and it acts like it creates something called a micelle. So what happens is you get globules of nonpolar stuff. Embedded within them are the nonpolar part of the soap
What
molecule,
is it called?
a micelle.
Is that what micellar water is?
What?
I'm not sure. And then, so this part is now polar on the outside and it can go into the water more easily.
Micellar
All right,
water.
now for the lab.
Oh.
So we're gonna do, you guys are gonna help me here.
does it
I'm gonna
make
need some
globules?
volunteers so that we can all make fun of you when you fail.
No, I don't want to.
Now, how's that for a resounding, hey, can I do it? I'll do the first experiment just to kind of get us started, and then I need some people to help me here. Okay? This should be done before you leave and turn in. I'm sure you'll be done and not have to worry.
It's double sided.
Oh! All right. So on the front, there's a bunch of reading, blah, blah. Just look down to where it says the experimental procedures. We're going to do a kind of surface tension test, a viscosity test, a vapor pressure test, and a miscibility mixing solution solubility test. At the bottom in the lab analysis, it also gives us what the possible boiling points of them are. And then the very bottom shows you what the three substances are in their molecular structures. We just don't know who's who. I have them labeled X, Y, and Z, and we're going to see if our experiments can reveal which is which. So, the first experiment, if you flip the page now on the back, we're going to basically just rank these from highest to lowest, where 1 means it's the highest value of that property, and 3 is the lowest, okay? So we're just
We're trying to
ranking,
figure out which one's which.
yes. So, first let's do the viscosity, because that's an easy one. So I have made 3 viscosity tubes labeled X, Y, and Z, okay? Now, with the molecular structures, okay, like I said, the main thing you want to start with is, well, based on their IMFs, could I predict which would be most and least viscous?
Yeah.
Right? And with that thought in mind, let's just look at the data. So let's test substance X's viscosity. Ready? And I'll do like races again if you think they're too close. Here's X.
You looked at them all.
Fast.
Okay.
It's not glycerin.
Pretty fast.
Pretty fast. Okay. Here's Y.
Okay.
That's
Faster.
fast.
That's really fast, right?
That's hexane.
Okay. And then Z.
Okay.
Oh, that's the fastest.
That's okay.
What did you say?
Okay.
So let's wait. I just want to make sure you guys understand the ranking system because every year somebody mixes it up.
The lowest viscosity.
What would be number 1, the highest viscosity?
Why?
Z.
Why?
The last
Oh,
one, the
highest
one you're holding.
viscosity?
Z.
Oh,
This
I
is-
see.
Z is your highest
Oh,
viscosity.
1 is highest, right?
Yeah.
I screwed it up.
One is the slowest.
So 1 is Z because it's highest.
And then 3 is Y.
No, 2 is
Wait, what?
2 is
No.
2 is Y.
So
no, no.
Y was the
3 is
fastest.
Y. 3 is Y.
So this had the lowest viscosity, so this is 3,
Highest
right?
viscosity is Z, right?
Yes.
The highest was Z, so it was a 1.
Sorry.
And then 2 was X, right? It was the middle one. All right, so that's an easy test. Done. For surface tension, I'm going to need some volunteers. Let me tell you what you're going to do before you
I have a
volunteer.
bold prediction.
Do you?
Yeah.
Because this one's a little harder to make work out.
Z is
Hold this.
glycerin.
Take this.
Yeah.
No, okay.
I shall now place 1, 2, 3 glass squares and 1, 2, 3 pennies, Lincoln side down. And I shall place X, Y, because I want to, and Z. And I shall next place 3 droppers. And I need 3 people to each count how many drops they can stack on the penny before it collapses.
Not it.
I'll do it, but can you bring the thing over here?
Which one would you like?
Z.
Wait, no, I got these right here.
Wow.
Fine, you do Z.
I can do
You do
Can I do X?
X? Callie, which one would you like?
What's left?
How brave
Why?
would you get up?
Yeah, how brave are you?
Here's X.
She's making the.
Don't spill it on yourself.
It's water.
Water's not one of the options.
water.
All right, while you guys are counting, and we wait
One.
with bated breath. Don't pretend, I heard that. I heard
I'm
that.
not even squeezing. I'm not even squeezing it.
Cheaters.
Kelly, stop! Look, it's
coming
not
out
even
the pipe.
squeezing it. It's just falling out of it.
Wait, oh my gosh. Why?
We learned about that.
Why is that happening?
No, it's
The
force.
capillary action. It's
capillary action.
No.
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 Surface tension.
Surface tension is one thing, but what if it also has a really high vapor
Mine
pressure?
stopped at 22. High vapor.
Think about it. If you pull it up in here and it tries to evaporate, that exerts pressure to push it out. And it has a, where are you going?
It has less
And it has a lower surface tension to hold it in place.
capillary.
All right, can you count the, oh, you dripped it everywhere, Kelly. Oh my gosh.
Broke it.
Yeah, it just fell.
Kelly, where you going?
Right, I'm done.
What?
My legs
Give
hurt.
up.
That's it? You quit?
I got
You
22.
count it.
I'll do it then. Watch it. Watch me.
You have to tilt it at an angle.
1, 2, 3, 4,
Did we figure it out already?
5,
I have an air bubble.
6, 7,
Why do I have
Eight.
an air bubble?
9,
Press
10,
those.
11, 12, 13, 14.
6 forever ago.
Which one
Wait.
is that?
Yeah, I think it fell. 14. I got 14 on Y.
I got 22 on
It didn't
X.
fall yet.
What?
22 on X.
X,
I got 27 on mine.
22.
If you don't have one.
What did I say? Y was 14?
I was 14.
Do I count the drop where it broke?
What's Z?
Kidding.
Yeah, how many?
You
33.
gotta have a
33.
Okay.
Oh my gosh, you guys actually got the right results. The other class was all over the place.
Bro, what is this? It smells.
Wait, so the
Bad?
highest surface
Don't
tension is the most
don't
drops?
keep breathing it. Here, give it to me quick.
The
Yeah.
highest surface
trying
tension
to-
is the most
No.
drops, right?
Oh, that's right. You
Is
breathed
this all
it.
because I called you ugly and stupid?
So mean.
So like.
Ladies and gentlemen, take a close look. Is it that bad? Am I that ugly?
I think you're back.
Is the most drops the highest surface
Well, it's
tension?
gonna drop on
What do
my
you
desk.
think?
Well, that's what I asked.
Well, I'm asking you what you think.
Can you
If I
take
knew, I
this,
would-
dude?
Oh, it's
Mr.
done.
Princess, you're the most handsome teacher.
Mr. Kretzo.
Oh, you still have it. Sorry.
I think it's on my desk.
Don't worry, it's gonna be gone in a few minutes.
Mr. Curiosity
That's
said that.
so rude.
Okay, anyway.
He was crying like a little baby. And
I was throwing your ears coming out.
Anyway, the question was, what does this mean? Which has the highest viscosity if it can make the...
No, not viscosity.
Wait,
surface
we're on
tension.
surface tension.
That's what I meant. Which has the highest surface tension?
Z.
Is it 33?
Why is this the highest? Because it stacks the most. Yeah. So this would have the highest, so that would be 1. This would be 2, and this would be 3. Okay. We did viscosity. Oh, evaporation. For this, I'm going to do what's called a streak test.
You can just guess. You can just guess.
Yes, but data is
We
more
have two
powerful than
trials.
guessing.
Oh, is that where you see like how much?
We could just
Yes.
look and inform.
All right. Who wants to be my guinea pig?
Yes.
All you have to do is watch.
Sophia said yeah.
Sophia can't see.
Yeah, Sophia can't see things. Here's X, Y, and Z. I shall now do a streak test. Who will watch? Here is X. Hafiz, watch the streak.
Wait for a little.
Okay.
Bro, everybody
What is it doing, Hafiz?
Yes,
It's like
I was in
barely
the car. I
Why
was
don't
like
you do it
laying
at the same
down.
time?
I was like
I guess I could do that. It's evaporating. Here is Y.
Super fast.
Not super fast.
No?
Oh, when we were in that one north parking lot.
It's almost gone.
Yes, I meant.
Is X about gone now?
Yes.
So who won that race?
Why?
Because I asked you.
Why?
Who won?
Why?
I'm asking you, that's
Thank
why.
you so much.
Wait, have you seen the video?
Why did you
All right, just for that, you have to watch this one. That's Z.
So why did you give the numbers like this then? Because now Z is gonna be 3, but it should be
Watch
1.
that.
Why?
Well, like, oh, does it not matter? Do they not all need to be the same numbers?
Well, hold on a second now. No, they don't.
Okay.
It's the rankings. So what did we just discover? Which one evaporated the fastest?
Why?
Y or X?
The fastest was Y, so this was, in terms of vapor pressure, the highest. I believe X was second, and Z was third. Okay?
Yes.
Okay. And then,
What is the other way around?
Miscibility.
what?
It's supposed to be the other way around.
No, vapor pressure is the one that goes the other way, right? When the forces are weakest, it evaporates the fastest.
Our numbers are wrong.
What do you mean they're off?
3, 3, then 1.
So what?
Never mind.
They're supposed to go opposite. That's my point.
Okay.
All right, now, miscibility. This you're going to have to split into polar versus nonpolar solvent. So I only gave you one box, but just cut it. All right, so let's look at which one, polar first. So let's look at them in water. So these are X, Y, and Z in water, and I added 1 drop of food coloring to each. Here's X in water. I'll shake it up.
Oh,
It kind of mixes and then separates.
wait, is that water at the top of the
The water is going to be where the green ends up. The clearer stuff is going to be the X, Y, or Z.
Oh.
So that's separating, but somewhat kind of mixing-ish. But still, you're getting 2 layers. So you see that X does not mix well in water. If we now look at Y,
That means it's not polar.
Oh, that's
But
soluble.
that means its miscibility is good or bad? It's high or low?
low. Low. When the miscibility is low, they do not mix well. So that means it's not very soluble.
It's not polar.
The substance is more non-polar because the water is polar. Y, here we have, again, separation. And if I shake them, I'm just trying to make the point they seem to separate faster.
That one was fast.
And that's kind of going back to what you asked earlier. But neither of these mix very well with water. But it seems like this one's even worse. This one seems to stay together longer. So to me, and I don't know if you're agreeing, but I feel like Y is mixing less well than X is.
So Y.
So that means Y is more non-polar.
Yes,
Okay.
I agree. And then Z, well, it's already fully distributed. So doing this doesn't do anything. You can see the color goes all the way through and there's no separation. So it indicates Z is polar comparatively, yeah.
Low miscibility
So
is
that means it
low.
has
Low miscibility means it does not mix well. And if that's true, oh, you're asking like to rank them? So what do we conclude then for miscibility?
Is it?
In first in the polar, in water, which was the most?
I said the most miss.
Highest was Z, because it mixes completely. And then the worst, I think we said was Y, and X was kind of intermediate. And then in nonpolar, let's find out. So X, and I did put a drop of green food coloring, but it kind of sat at the bottom. By the way, the solvent is mineral oil. So this is in mineral oil, which is another nonpolar substance, or mixture really is. If I shake them, it basically stays mixed, but the food coloring, which mixes well with the water, does not mix well with this system. So you don't see the green distributing. Okay? So this shows that it is miscible in a nonpolar solvent. X is miscible in the nonpolar solvent. For Y, well, I don't know yet. For Y, I don't know. I have a hard time really distinguishing these. The best I can say is how clearly the little bubbles clear up, because the bubbles are really little balls of the other liquid mixing. So like if I shake this one up versus if I shake this one up,
Y stays green longer.
I think X is fast.
I don't know that the green is really telling me a lot. I get what you're saying, but I can't, which ones?
The
Here.
bubbles dissipate faster than X.
The answer's supposed to be.
They do? Here, let me do them at the same time. Ready?
Is that right?
No, we go way faster than the green one.
Why is the green one so green?
That I'm not sure. Maybe I dropped more than maybe I put more in this one. I don't know. This is like stuck to the glass. Oh, here we go. Maybe that's why it was sticking to the glass. That's weird. because the glass is more polar.
Miscibility and non-polar.
I mean, the best I can come up with to explain this is this clears up faster. Not the green, but just the bubbling. And I'm not sure if you agree, but
Is the green one Y?
yeah, but I don't know why the green is doing what it's doing. This is kind of complicated. And like I said, it's not always, solubility is not always a clear-cut definitive. So I'll let you guys decide which way you want to rank them. What do you think?
X is 2
Don't you
because
just keep
it's 2
two the
everywhere
same
else.
and
Yeah.
then switch Y?
X, Y, Z. So you want to call this 2?
Yeah.
And then 1 and 3.
1, and you think you're expecting this to be the least? Let's see what it
Wait,
looks
how are
like.
we putting that into our thing?
Split your
So you
box.
have to split the box because there was only one. So one for polar, one for non-polar solvent.
P and P.
So here's the Z. The Z shows clear separation of layers. The water, or well, it's not water, but the layer that shows the food coloring is clearly the more polar side, and then the one that does not is the less polar. If I shake them, they will temporarily be distributed to each other, but they will on their own separate.
Oh.
Well, that goes again back to the properties. See
Maybe.
the viscosity of the green layer.
It might.
Okay, so I think that was the last test. So now you should be able to complete this paper and turn it in. While you're doing that, I'm going to give you problem set 2 for Monday. All right, so tomorrow you guys have problem set 1 done. We'll do some questions on it. But you need your lab books tomorrow. We're actually going to do a quickie lab called, or based on chromatography that relates to this.
Another problem.
Is this due at the end of class?
The lab you should finish, just get off your plate. It should take you 10 minutes, which was what we had.
Formula?
Which side is polar and which side is
Monday
non-polar?
for
What is that?
What?
Which side is polar and which side is non-polar?
C is glycerin.
The left group is the polar solvent, the right group is the non.
So here, do we write the molecule?
Yeah, just its formula from the front. The chemical formula, just the,
Oh. Okay.
Can we just write its name?
I
well,
would put glycerin. It's C.
wait, are you looking for the boiling points?
C.
Oh. It's on the front.
We don't know what we're.
Those are the.
It's C, whatever, H, whatever. C, whatever, H, whatever, O, whatever. You just count the atoms.
C is 3 C's, 2 C's, 2 C's.
No, just write it in the computer.
So then the second,
Right, I'm so tired right now.
and which one is hexane?
While you guys are working, I gotta clean up. Yeah.
What's the ethyl?
Oh, just give me a few minutes to clean up and then we can check that out or otherwise.
C4, what? C3H8O3. Do we have to redraw the word structure?
Yeah. I want it in front of you so you can use it to determine the IMFs and all that. And so my plan is to give you guys a package of all your exams. I'm hoping to give it to you tomorrow to use to study for the finals.
X is the hexane is blind.
Copy the instruction on our site.
Yeah.
Okay, you can. But I think these would be
Wait, so is substance Y hexane?
What?
Is substance Y hexane?
I can't hear what you're saying, I'm sorry.
Is substance Y hexane?
What do you guys think? Did we agree on the which is which yet?
Yep.
Which do you think is which? X, Y, and Z?
Z is definitely the
Glycerin?
Glycerin.
Is X hexane because you said it's healthy?
I don't know, what do you guys
I
think?
said
No, Y is
hexane.
hexane.
Y is hexane?
Yeah.
Based on the properties. And X would be ethyl acetate. I mean, again, there's some of the data might not corroborate that directly, but the overwhelming weight of the evidence, I think this is the right order, based on intermolecular forces.
This one has.
I think I'm going to end the video now. Thank you for watching. Sorry if it was a little confusing from that distance, but thank you. I appreciate your attention.
He's gonna watch it.
I don't even know how to stop this thing.
So this is.
Is this thing on?
What's IMF's price?
Oh my gosh, has this been recording?
What if it wasn't?
Oh God. I can't tell if it was.
It wouldn't be our funny joke.